Okay, taking a look at page 2. Here's a theorem. If f is differentiable at x equals c, now we've seen two examples from the front side of the notes where functions were not differentiable at a specific point. This theorem states that if f is differentiable at x equals c, then f is continuous at x equals c. That's bold. This is a bold idea, which means this guy's really important. I want you to think back to chapter 1. There was an example problem in chapter 1 that I said, hey, this is an old AP free response question. It was a tank filling problem. And in that problem, we had to use the intermediate value theorem. One of the requirements of intermediate value theorem is that the function is continuous. But the word continuous did not show up anywhere in the problem. However, this word did show up. We were told that the tank fills, the function that models the fill rate is differentiable on its domain. Well, that told us that it's continuous. Okay? Couple of key points here. If I tell you a function is differentiable, that also means it's continuous. However, if I tell you that a function is continuous, that doesn't necessarily mean that it's differentiable. We've seen two examples. Y equals absolute value of x and the cube root of x. Those functions are not differentiable at x equals 0 for different reasons. Last but not least, if a function is not continuous at x equals c, then it cannot be differentiable at x equals c. So if you have a function with a jump discontinuity, it's not differentiable at that jump. If you have a function with an infinite discontinuity, it's not differentiable at that vertical asymptote. Okay, let's move on. I'm going to tell you about derivatives that fail to exist here. Some of them we've already talked about. I'm just going to put some more language, the language of calculus around them. But first, I have to introduce a couple ideas. I want to introduce some terminology. You may want to write this in your margin. LHD stands for left-hand derivative. And it means the following. The limit as x approaches c from the left of f of x minus f of c all over x minus c. Again, this is that alternate form of f prime of c, but now I'm just looking at it as a left-hand side. I'm also going to refer to RHD, which will be our right-hand derivative, and that is equal to the limit from the other side as x approaches c from the right. Okay, let's go back to our examples on page 2, derivatives that fail to exist. So this guy right here is y equals the absolute value of x. At x equals 0, it's not differentiable. Why? Well, first of all, what's the feature of the graph at x equals 0? We call it a corner. And at that corner point, the left-hand derivative at x equals 0 does not equal the right-hand derivative at x equals 0. So that's why we say it's not differentiable at x equals 0. Again, the feature of the graph is called a corner. The left-hand derivative and the right-hand derivative, they were not equal to each other. In fact, the left-hand derivative was -1. The right-hand derivative was +1. Those two values don't equal each other, therefore that limit does not exist. Anybody know what this next feature is? What it's called at x equals 0? By the way, this is the graph of y. It's not an absolute value. It's a function that really we use for this sole purpose. I call it the seagull function. You see? Look at it. Do you see it? It's kind of charming, isn't it? It looks like a seagull in flight. Hopefully it's not an albatross around our necks. All right, so that's y equals x to the 2/3 power. Okay, that is the classic example of a graphical feature called a cusp. Okay, so a cusp you might think of as, oh, it's kind of like a gradual corner. It kind of slopes down to the corner. But it still gives us a place there where we can't draw a single tangent line. Okay, by the way, x to the 2/3 power is the same as the cube root of x squared, or the cube root of x quantity squared. So that's what that 2/3 power means. That's just a representative. So this is kind of, I guess I'll call it, we'll call it an extreme corner. Okay, and here's why. The left-hand derivative does not equal the right-hand derivative at x equals 0. Think about this. As we're coming in here, we have a negative slope, but it's getting more negative, more negative, more negative. And for those of you viewing at home, you can't see that. So as I enter the graph here, it's getting more negative, more negative, more negative, more negative, and my slope falls off there. And then over here, my slope is positive, but it's getting steeper and steeper and steeper and steeper as I go towards x equals 0. So let's talk about this. The left-hand derivative at x equals 0 is equal to negative infinity. So if I draw tangent lines on the left-hand side of that graph, and they get closer and closer and closer to x equals 0, those tangent lines are going off towards a slope of negative infinity. But the right-hand derivative at x equals 0 goes off towards positive infinity, because the slope instantaneously changes from negative to positive at x equals 0. Okay? So, again, not differentiable at x equals 0. X to the 2/3 is not differentiable at x equals 0. Our third and final example here is a vertical tangent. And for vertical tangent, we have f prime of c is equal to positive infinity. And as we reviewed on the previous page, the slope is undefined. All right, this brings me to a point now where I want to review terms from Chapter 1. We talked about specific types of discontinuities in Chapter 1. Some of those we are seeing again here. Okay, discontinuities that we learned about in Chapter 1, the jump discontinuity. We also learned about the point discontinuity and the infinite discontinuity. For an infinite discontinuity, that turns into a vertical asymptote. So for all of these three ideas, I want you to refer back to the very important idea at the top of the page. Okay, so I want you to look back to the top of the page and answer the following questions. If I have a function with a jump discontinuity at x equals 3, what can you say about f prime of 3? It's not differentiable. F prime of 3 does not exist. If I have a point discontinuity at x equals 7, what's f prime of 7? It does not exist. It's not differentiable because that's a point discontinuity. If I have an infinite discontinuity at x equals 11d7, what can you say about f prime of 11d7? Yeah, it does not exist. It's not differentiable at 11d7. That's my favorite number, by the way, 11d7. Okay, so again, those ideas, if you have a discontinuity, the function is not differentiable there. Kind of makes sense. If the function has a jump or has no definition at a specific point, how could you draw a tangent line? Okay, next thing we're going to do, this is an extra problem. I would like you to graph f prime for each of the functions below. There are 4 of them, 1, 2, 3, and 4. And then when you graph f prime, I want you to explain your thought process to me. Go. Folks, this is a thought process, and you deserve better. First graph here is a linear function. It has an x-intercept of 2. It looks like it has a y-intercept of -4. That would probably be about a 4, like a slope of 2. Okay. What does my graph of f prime look like? All lines are straight. This does not have a slope of 0. Oh, a straight line, like, hold on, a straight line at 2. Like if this is 2 and this is 2, like this, that's, oh, horizontal, yeah, okay. Now I understand. So it's a horizontal line at y equals 2. So this is my graph of f prime. The derivative is a constant. If you have a line, its slope is constant. Therefore, its derivative must be a constant. Okay, second example. This graph of f looks like y equals -4. That's the graph. That's what f, the function, is. What does its derivative look like, Jeannie?
Oh, whoa, hey, that was a violation.
Y equals 0. Tell me why that makes sense. The slope of this line is 0. A horizontal line, don't say it has no slope. It has a slope of 0. When you say a line has no slope, I don't know if you mean it looks like this horizontal or like this vertical. So let's be specific. Its slope is 0, therefore its instantaneous rate of change is 0. So there's my line y equals 0, which is my graph of f prime. Okay, next one. Uh-oh, this is creepy. It's a parabola. It's got a vertex at 4, 0. So if I were writing this out as a function, I'm going to assume that the stretch factor is 1. It looks like it is. I think it would look like the quantity x minus 4 squared. Does that ring a bell? Is that right? Okay. Any ideas there about what the graph should look like of the derivative? This one is trickier than the ones you've done previously. Thoughts? If we think about the behavior of this function, and I'm right here, is my slope positive? Slope of the tangent line, is it positive? Is it negative? Is it big? Is it small? That's a question. It's negative, and it's a large number because that's steep. So it's a big negative number. If I move that point to here, is the slope of the tangent line still negative? Yes, it is. Is it smaller? Well, I went from a tangent line that looked like that to now it looks like that. So that is going to be a smaller negative number. So it's less steep, if you will. What about when you get right here? Yeah, the tangent line is horizontal. It's got a slope of 0. So I can absolutely put a point on the graph of the tangent line right there. Now, as I move over here, as I move this point to the right, the slope is now positive. And as I move farther to the right, the graph gets steeper and steeper and steeper. Guess what, folks? The graph of f prime of x is going to look something like that. The instantaneous rate of change of a quadratic function is a linear function. Last but not least, let's take a look at absolute value of x. I think this is f of x equals absolute value of x minus 4, that quantity. We've already kind of seen this one.
Student in the back name, we'll call him Ryan.
No, you weren't.
If you put your hands up, I'm calling on you.
It's an unfortunate coincidence that the international symbol for I have a question looks like I'm stretching. The slope here is negative and it is a constant. The slope here is positive and it is a constant. So at x equals 4, my behavior changes. Positive constant right of 4, negative constant left of 4. And this value here is 1, and this value here is -1. Folks, that's it.